Okay, we're reviewing Kirchhoff's voltage law, and we want to solve this particular circuit. And we have two questions. One, we want to find the voltage across the 20 ohm resistor, called VR2. And then finally, we're going to be asked to solve for VC, which is the voltage across the current source. For this, we see that we know the voltage for the voltage source, and initially we don't know the voltage for the resistor, but we do have both the current and the resistance, and so we can get the voltage there. With those two voltages, we can use Kirchhoff's voltage law in order to solve for VR2. So, first of all, we're going to define a voltage, and we'll call this V50. Just because it's on a 50 ohm resistor. And with this, we have the passive sign convention such that the current is entering the positive node. That's how I knew to put the plus on the right and the minus on the left. So for that, we can find V50. And V50 is just going to be equal to 0.471 and then times 50, and that's going to be equal to 23.6 volts. All right, so now that we know that this is 23.6 volts, we're going to go around the horn, and we're going to choose to do the form sum the drops. So we're going to start down here, we're going to go around clockwise, and then let's identify this is going to be a rise, and then this, we go from minus to plus, this is going to be a rise. I'm not going to write rise on here because it's going to be a drop when we go to the left-hand side, and it's going to be a rise when you go to the right-hand side. So we'll just acknowledge that for this particular mesh, then this is going to be a drop. So we're going to need to have minus this, and then plus this. So the formula would be, since this is a rise, we're going to get minus 7. And since this is a rise as well, we saw that the voltage V50 was 23.6, so we get minus 23.6. And then finally, we hit the plus sign, so it's a drop. We can say plus VR2 is equal to 0. This is KVL. And that's KVL for drops. Then we solve for this and we get VR2 is equal to 30.6 volts. Now, we will just go ahead and label it. This is 30.6. So we've solved for VR2. Now we want to solve for VC. Well, we've got the voltage here. We need to solve here, but we don't have the voltage here. However, we do have the current. We realize that since this is a single leg of the circuit, the current here has to be the same as the current here, which is the current here, which is the voltage source. So that's the current source. So this is 2 amps. 2 amps goes to the left, 2 amps goes up, 2 amps goes to the right on the bottom. So this is 2 amps, which means we can find what V100 is. We'll call it that. And so the current enters the positive node. So we've got that. So we'll calculate V100 is just going to be the voltage, is going to be the current 2 times the resistance, which is 100, which is 200 volts. That's a lot of volts. So with that, we have 200 volts. Now we can write Kirchhoff's voltage laws. We'll start down here at the ground symbol, reference node symbol, and we're going to move around. So here, this is where I'm going to sum the drops. Here, well, this is actually a voltage rise now in the second part of the problem. And then VC, that's a voltage rise. And, oh, wow, for V100, that's also a rise. So if we do the sum the drops, we're going to get negative, negative, negative for each of these. But no worries. Negative 30.6 minus VC minus V100, and we found that V100 was 200. 100 is equal to 0. Well, we're going to take the VC over to the other side. So we'll have VC equals minus 30 minus 200. So VC is equal to minus 230.6 volts, and we're all good.